Right, so in today's lab we're still not going to look at directly at graphics. We're sort of going to look a bit at debugging because we got the impression that you guys were not as familiar with it as you probably should be. I asked you to come up with some cases that I could use as examples, and no one came up with anything, so I just basically threw together or stole one from the curious recurring bugs at Facebook. So for you people who watched that video, don't sort of answer at least straight away for this first one. The other three bugs that we're looking at will be some bugs in my code and some bugs in some other people's code. The code base will be unknown to you, but that's also something you need to be sort of prepared for. That might happen later anyway. Originally I was thinking of trying to find a way to sort of show you how the debugger works, etc. in a sort of constructed case. But I couldn't actually find a sort of proper case for that, so we're just sort of jumping straight into it.
Can you zoom in a bit? And just, can you increase fonts a bit?
So also, if you ever have trouble seeing or need me to clarify something, then just say so. Yeah. Okay. So yeah, we're going to look at debugging. This program has a bug. I'll just quickly explain what the program does before we get to that part. This is the one like really constructed case that I came up with, so it doesn't actually lead to anything. It's just sort of a thing you should. Yeah, it's just an example, which can also show how C++ can sometimes make you trip up a bit. Sort of the case that we're looking at is that you're running a server, so we can have a last server, which takes in a standard map, which is basically a hash map. I think you've learned that in the algorithms course, so that you can index based on strings, with settings, which we will then use to sort of configure this hypothetical server. Which we just reload sort of the settings that we are going to apply to the server, and we would also be doing that in sort of the real case. So everything else is sort of omitted, it's just the logging that we keep here. The way it works is that we essentially just read the file, open the file, and read through every line in the file, and the file looks like this. So essentially we just split the string at or for each line we just split the string at the middle of, or at the column, and then, the right-hand side of the column is the actual value, and the left-hand side is the name of the value. Any questions? Nope. Cool. So now it runs sort of correctly. Now it runs correctly, which means that we get out the values that we say we're trying to get, which is impossible for everyone to see. But
there's program properties.
Yeah. There, that's better, I guess. So yeah, so with here you can see that we get out the same as we have in the settings files, which is the socket timeout of the server IP, the server port, the socket timeout, etc. And we also print out the number of settings. So the example that this is based on, this is the one from Facebook, is imagine that we refactor this sort of code, or someone goes and factors some code somewhere else, and we decide that we don't need the socket timeout anymore. So we'll just delete that from the from the file, and then we will see what happens. First of all, is there any guess as to what will happen?
It's a default value.
Okay. Anyone else?
Without looking at the code?
No, you can look at the code.
It complains and throws a temperature.
That's a possible solution. or total output. Yes, it actually does what you said it does. It gets a default value. And the way that we could sort of observe this, and this is where we sort of get into the breakpoint aspect of it, or at least first see how it invokes. So if we look here, we'll get the peculiar thing that we have our socket timeout, which doesn't have any values at all, and apparently we have 3 number of settings, which is quite confusing. So let's try to figure out why. So what we'll do is that we'll set a breakpoint. So for you who don't use Visual Studio, it's essentially the same in other IDEs, at least as far as I experienced. So it's obviously somewhere sort of here along the lines that we get our issue, so we'll just jump straight into it instead of breakpoints. By the way, I'm to sort of try to make this not too Visual Studio specific, and to make it a bit more challenging for some of the sort of later bugs that we're looking at. We're debugging this in release mode rather than debug, mainly because in some of the other cases, Visual Studio, or they will actually sort of notice the bugs that we are running into and just straight up terminate at that point and say, like, here's the line where the bug occurred, which that's great, but that won't sort of help you get into the mindset of doing the debugging. It's a bit more help than more. So that means that we will be debugging in release mode, which has the cool benefit that suddenly all our variables are optimized away because they don't need to sort of exist. Like the buffer variable up here is optimized away for various reasons. But cool. Okay, so yeah, I've set a breakpoint and I've run to the breakpoint. Setting breakpoint, just click on the side and just run and it will stop when you get to the breakpoint. Down here you have a sort of overview over all the variables that exists within your application. So, or sorry, within the local scope. In this case, we have our settings, and this is probably super hard to see for anyone who's watching. Watching at home, but that's why you should show up to the lectures. So the settings, it has 2 variables. It has a server IP, which has the value of the IP address, and the server port. And there is no sort of third variable here that is named timeout. So timeout. Yeah. So we want to figure out where that sort of variable came to come from. So what we'll do is that we'll step into this function using F11. And we'll see now that we suddenly jumped up to our server class. Looking at, and we can look at the input parameters. It's still what we expect it is. It's still 2 settings. And then we'll, yeah, and this is sort of where it gets fun. We'll jump around a bit. We'll initialize our settings in the initialize list, so that now we will have our M settings map, which still holds the same values. It's just a copy of the original one. And then we're printing the settings. And if you look at, you can see now suddenly that it turned red down here, meaning that something's changed. So we did one step. Or we sort of incremented one step, executed one step of code, and suddenly we have changed our M settings, and now it says that the size is 3, which is sort of weird. And that's the socket timeout. So suddenly it has appeared. You can try to run it again, and so because you need to try to figure out where stuff goes on, and in this example we're not going to go that deep because I don't want to go into the standard library on Microsoft because it's sort of scary in there. But what I essentially do is that you sort of step into functions using F11, and if you step this far, then if you start seeing constructs like this, that's when you're stepping into the standard library, or close to it. Yes. No, it's still a standard library, it looks like, at least. And usually at your sort of programming levels, the error will not be in here. Because these things are, quite well tested and implemented by relatively smart people. So what we do is that when you get to this point, you'll sort of accept that the problem is probably not there, and then you'll click Shift F11 to go back out again, and sort of continue stepping on. And yeah, so obviously what we're seeing is that at some point before the printf and after the printf, we have changed size and added the extra value. And that is, as Jürgen said, it's because we get a sort of default value for end settings, which also is documented in the CTP reference, which is why you should read there. I just brought it up because it's super confusing, and as the Facebook guy, or the guy holding the curiously recurring bugs at Facebook mentioned, they receive a lot of common bugs arise because the way stud map works, in that if you sort of try to use the square bracket operator to retrieve an element and that element doesn't exist, it will actually insert it into, or insert a default value into the map, which isn't what I've seen a lot of other languages do. Cool. So any idea how we can fix this?
Well, even if it doesn't fix the bug, you're currently referring to socket timeout, that can't be being used, so you can just remove that.
Yeah, that's one way. So just yeah, because we're not using it at the moment. So let's pretend we were using it. Let's pretend we sort of did some socket logic afterwards. Yes.
.at.
Yes, that's one way to do it. So one thing you could do is instead of saying the square operator, we can say .at. Which will sort of look for the item, and if it can't find it, then it will throw an exception. Yeah, which it hopefully will do now. Yeah, and handle exceptions out of range. Cool, so that's one way to sort of fix it, or at least not fix it, but at least sort of not get the bug that we originally want to, or would want to get. Because getting an exception or getting told that something is wrong, that's way better than sort of trying to figure out later why your socket suddenly never times out. Which is also why I talked about the asserts sort of yesterday. Cool. Another way to sort of mitigate this is if we, instead of, because you've all seen const, right? I know when I did my fagfadder for a lot of you guys, I went on rant about how you should use it often. That's also something that could help you in this case. So if we, instead of using our, if we rather than using just a copy of the original settings, we take a const reference to it, then we'll see that we'll get a compiler error when we try to modify using the square bracket operator, because in that case the square bracket operator may modify the map internally, so it's checked at compile time that we're not sort of calling in methods that might modify the map. Everyone got that?
I'm still with you.
Okay, cool. So yeah, in general, try to use const, because this, in C++, const is proper. It's not like the final stuff that you have in other languages, where it's like it protects you from just one sort of single bit that I don't really think you need that much protection from. Because the way const works in C++ is that when you mark an object as const, that also means that you're not allowed to call functions that will mutate the object. So it's not like Java, where if you have a sort of, say, a final parameter in a function, then you're allowed to call functions that modify that parameter. You're just not allowed to reassign it, which means that it's not immutable in any sense of the word. It's just you're not allowed to reassign the reference. However, with const, you're sort of you're not actually allowed to modify the object either, which is really helpful, and it's also really cool for the people calling the function to read, to know that you're not modifying the values that I'm sending in. Unless you do really dirty stuff, but I'm not going to sort of discuss that.
You might want to, well, you can also only call member methods that are marked as const.
Yeah. Yeah, so that's the second point. When you create methods, sort of like, let's say, int get or get number of settings. And then we just like return. So if I were to have, let's say we'll just remove this here at the moment. If I were to have a const server like that, and I would say, number of settings is equal to server.get number of settings, then this won't compile because I have a const. I have a const server. I'm trying to call a function on it that's not const, which the compiler can't guarantee that we're not mutating the variable. So what we'll do is that we'll set this as const as well, which means that this function now gives a guarantee that it won't modify the internal variables when you call it, with certain exceptions. But again, dirty exceptions, so you can always assume that when you're calling it, you should never be able to see any potential modifications that happen behind the scenes. And in general, breaking the sort of const rule of having a function marked const and then changing member variables on the inside, first of all, it requires extra syntax to do it, and secondly, it's really bad. You have a question?
That was basically the question. Could you set the function as const and have it change the thing over the compiler?
The compiler will complain. So if I now do, for instance, msettings dot, let's just try to say like counter is equal to 0, then that will complain because we're modifying that. However, if we're doing it that way, then well, it won't there. It won't complain because it's this function has been marked as const. Again, it's C++, so there's always ways to get around this, but in general, that's considered bad practice. But that's something you should keep in mind because stuff like const can really help you ensure that you're sort of avoiding at least some certain types of bugs. Cool. So that was fast, and that was the sort of first example with a sort of more contrived way of working. So let's look at some of the bugs that I faced using or developing the GFX stuff that I created for you. Let's see, where is the actual source here? There we go. So just sort of showing the correct implementation to show how stuff works, so that you know what you're supposed to see. All right. Cool. So then the question comes, which bug do we start with? Okay, I guess we can start with so this is how the program is supposed to function in sort of originally. We're sort of noting down all the shader programs that you have in your code and all the vertex array objects. You'll get to know what they are soon. It's not important for the sort of topic at hand. But what we do is that we get some variables out of your shaders, and then we are able to sort of look up the code that you're using to program your shaders. And the other thing we're doing is that you can see there we have like 2 shaders with different variables, and we can open them and we can inspect their source, which at this point is identical because there's limits to how many different types of shaders I want to sort of create just for testing. The other thing that we can do is that we can inspect sort of buffer objects. So essentially, when you created your triangles, you created buffer objects containing sort of the vertices that you're supposed to draw. We are also allowing you to sort of debug those. And the way we do that is that you send in sort of a unique ID, and then we can give you some information about the objects that you created. So we can show you what sort of stuff you have in your element array buffer. We can show you the different attribute buffers you have. The most important thing now, again, is not that you see that you understand everything I'm talking about. It's that you see what's going on screen. So yeah, we can open all this and we can get data out, and we'll see what sort of type we have, how many dimensions your data has, the size in bytes, etc., etc. So everyone sort of got the understanding of how then this is supposed to work? So the gist? Cool, then we'll switch over to the bug version. So we have some different kinds of bugs. We can start with the most critical. This is a problem. I can't show off all the bugs because that will crash the program. But we'll start with what I know to be one of the more major ones, which is that when I now open the VAO and try to draw my context, or sort of draw the contents of a buffer, we suddenly don't get any values at all. That's the bug. So this is sort of where I want to switch to interact mode and ask you how the hell do we fix this? Yes?
Breakpoints.
Cool. Yeah, we can put a breakpoint. Where do you want to put the breakpoint?
In the function that checks the VAOs.
Okay. So the function that checks the VAOs, that's this one, the introspect vertex array. So we can go and put a breakpoint in that. Where did my solution explorer? So that's
Just click it and press F12 to go to the pen.
yeah. Right, so we set a breakpoint. Here we are. What do you want to do?
Run the program, step through it.
Right. So cool. We start stepping through the program. And this is also where it gets fun, since we're doing this in a release mode. You'll see now that I pressed F10 and then suddenly we step back up again. This is us meeting sort of optimized code. So if it can reorder our instructions, or the compiler can reorder our instructions, then it will probably do that. If it can find a sort of more efficient way to call functions, etc. There are certain rules as to when it can and can't do it, but that can make it a bit confusing to do debugging in release mode, which is why you, if possible, should avoid doing it. But sometimes you have to, because you can get certain bugs that will only manifest in release mode, and then everything will work fine in debug mode, and then you don't really have the choice. Yes?
What kind of bugs?
Undefined behavior bugs is a classic one. Yeah, that's a classic one, which will, or that's often the other way around. It will work incorrectly in release, but it might sort of throw an exception in debug, or sort of tell you about it at least. But also certain race conditions might also just happen in release mode. They can in general be quite random, so yeah. Or you might also be in the case where the program isn't executing fast enough in debug mode, and then you don't really have a choice either than sort of switching over to release mode. But okay, so if we continue to stepping, what we're seeing is that we're sort of reading a bunch of variables from OpenGL. And we're yeah, finding a lot of stuff. Is there anyone who sees anything that they find interesting yet? And then we suddenly jump. So the reason that we did a jump here is because in GUI, it's collapsing header. It's basically the blue bar that we opened. That function is responsible for creating the blue bar, and if it doesn't open, well, it doesn't return true, so that's why we're just sort of skipping around here. Cool. And then we're starting our for loops to iterate through all the vertex attributes. Starting at the 0th one. Checking if it's enabled. If it isn't enabled, then we just go on to the next one. And then we create sort of a new collapsing header, which is another blue one. Yes?
Should it have anything to do with that you have a fixed size buffer? Or is it big enough?
Do you think it has anything to do with the fact that I have a fixed size buffer?
If you're missing characters, then maybe it's cool.
It's a good suggestion. The thing is, though, that we're this buffer is 127 bytes long, and we're just writing attribute and a number into it. So the chances that we're sort of going out of bounds is not, or is really low. It is a possibility theoretically, but it's not practical for this case. Because I don't know exactly what the number of maximum vertex attributes you can have attached to one. I just know that the standard says that it has to have at least 4. And my computer is not that old, and I have 16, so I'm just assuming that's a sort of reasonable number to iterate through and sprint that into the buffer. Because like the chances that we'll get numbers so far that we will, or so big that we will sort of break the buffer, that's really, it probably won't happen. Cool. So I can give you a hint if we switch over to the debug mode, if people sort of want that. Anyone want to see switch over to the debug mode?
Yeah, sure.
Cool. Just see if the bug manifests properly first. Cool. So that's you know, now something else happens. We switched into debug mode, and then we got an exception. By the way, this isn't like standard C++ exceptions. This is like, you know, the Windows throwing exceptions for you, so you can't really catch this, or you shouldn't catch this. It's sort of runtime checks in debug mode, etc. But yeah, it says runtime check failure to stack around the variable offset was corrupted. So what do we do with that information?
The variable offset.
Cool. And then
The breakpoints.
yeah. So we're at offset. That's the value of 0. So let's take a step and see what happens. Cool. Sorry, we were not supposed to go back to debug mode because it's actually easier to see in release mode. However, you got the hint that you need. There's some stack stuff going on. But we sort of have gotten information here. We've seen that there's something to do with offset and the stack being corrupted. So let's try and figure out, you know, how and why and what changes. So we'll still keep the breakpoint here because that's still correct. And click. So here we are at the offset variable. what we can do is that we can mark a couple of variables here that we think might be interesting. So my working theory, because you should sort of try to have theories around this, is that we're sending in a lot of pointers to different places, and I think we're going out of bounds somewhere based on those pointers. So what I'll do is that I'll sort of add a watch to all the variables that is defined in this scope, because it's probably one of those that, like, if we're going out of bounds and sort of disrupting the stack, it might be because we are sort of, yeah, writing to a variable of sort of incorrect size and then going over and writing to another variable. So we can just add watch here, so we'll get a list of all our variables. So the reason I'm switching over to doing the add watch is basically because looking at sort of the local variables, it's too much stuff going on in here. It's too many variables, and half of them are optimized away anyway. So it's, you know, that makes it even less fun to try and see what's going on. So that's the size, that's the stride, that's the offset, and usage. And then what we'll do is that we'll sort of do this function and see what changes. So I executed the function. Did anyone notice anything change? Yes?
Offset and type became 0.
Yeah. Offset and type became 0. And the offset, that's sort of understandable, because that's the value that we're sort of sending in to be modified. However, there's no reason for the size to change, or sorry, the type to change, because we sort of decided that way up here. So there's no reason for that variable to change. So that's sort of weird. But that also explains the behavior that we're getting later, because when we actually go into the, when we actually click and go into sort of visualizing the buffer, what we're doing is we're switching on the type that we get out from OpenGL and sort of printing out either, you know, numbers, or we're usually printing out numbers, either like unsigned or signed or floats. And none of the enum types we have here is probably 0, which means that this switch, which also doesn't have a default case, will just fall through and nothing will be printed, looking at sort of the data. So that sort of explains the behavior. Then the question comes, we've sort of identified the symptoms and sort of explained the symptoms, but we have not really gotten to the root of the problem yet. Or we've obviously identified where stuff goes wrong, it's here. Then the question is trying to figure out, why does this go wrong? We can try to enter the function. So that's F11, which we're not allowed to enter it because we don't have the symbols for it. Because this is usually just a function pointer loaded by glue, which we link to, so we don't have access to go into that, I think. Yeah. I assume it is. Yeah, it's a bit harder to get into this one. Any other suggestions?
Another question.
Yeah.
Stride, variable stride.
Yeah.
Is that the size of how much memory the vertex buffer object takes, or what is it?
It's we'll get into it once we get to the actual GL code.
Yeah.
Yes.
Is it the where cast the double pointer?
It's
or is that just unnecessary?
You're actually correct. It's the wave cast, the double pointer, or the void pointer. So I guess I could just sort of give my theory as to why this is happening. Because this actually happened. It happened on the when I was developing this this implementation. It's fixed now, so you won't get that issue anymore. Because if we go, so what I've been doing so far is that I'm getting the buffers with GL get buffer parameter IV. So if you look up that function, then you'll see that this function takes it returns the parameter of a buffer object, and it takes a target, a value, and then a pointer to data. And what it does is that it returns the requested parameter, which is super great documentation there. But essentially, it takes in a pointer, and it's the reason you're supplying a pointer is that it writes to the pointer that you supply, which is why we're sending in the address of everything. However, if we look at the function I'm calling there, which is suddenly a different one, the get vertex after pointer v, says here that it returns the address of the specified generic vertex attribute pointer, and it takes a void double pointer. So for those of you who don't know what a void pointer is, you're familiar with int pointers and all character pointers, etc. You've been through this in OO. A void pointer is essentially a pointer with no type. So at least that's my understanding. So essentially it can point to anything, but the rules are you can never dereference it because you don't know how big it is. So you sort of just have to cast it over to another type of pointer. However, I think they said somewhere here that it's, or at least I read it in the wiki, I think, that it's legacy reasons that they take a void pointer here rather than sort of an int or something else.
Why double pointer?
Why double pointer? That's a good question. It's essentially it wants, that's sort of where this gets a bit weird. And this is me sort of going off on what I think is happening, so not the sort of the necessarily correct explanation. But essentially the way I see them treating this is sort of that they, it's sort of like they're sort of expecting you to send it an int, but they didn't go for an int pointer somehow, because they're sort of treating it like an int pointer, or anything else. You're sending in a pointer and then they cast it to somewhere else, because you don't have to necessarily, you can't store regular integer values in the pointer. It's just not always smart. So they'll sort of just take in the pointer and then they'll write their integer value into the pointer. So you sort of treat it as an integer, or at least I treat it as an integer when I get back. But they wanted to supply it as a void pointer. I'm not entirely sure the rationale behind that, but it's still something we have to sort of keep in mind. And my theory as to what's actually is happening here, or with that explanation, is there anyone who has any idea on what's actually happening here?
Yes. Maybe if they dereference it, then the pointer is 8 bytes if it's 64-bit, and then the int is 4 bytes, and then it overwrites both.
Exactly. So what happens here is that I just went like, well, if I'm going to treat it like an integer anyway, I might as well just create my type int, and then send in the address of it and just cast it to a void star or a void pointer, because then they still think that they get a void pointer. However, I sort of failed to take into account that on 64-bit systems, the size of a pointer is 8 bytes, while the size of an integer is usually 4 bytes. Which means that I sort of supplied them with, or at least GL int is 32-bit. I'm not sure if integers will always go by it. But at least GL int is sort of guaranteed, I think, by the standard to be 32-bit. So I sent a 32-bit pointer value into a function that expected a 64-bit value. So what will then happen is that everything is all our variables are declared on the stack, and we have no protection sort of going on in here. So what will happen is that when they start writing into the value that they get from me, they'll overwrite another variable or somewhere else on the stack. In our case, it overwrites the type value. When I ran this on Linux, it overwrote the dimensions value. So it's sort of, yeah. Did everyone get that?
Memory shenanigans.
Yeah. The reason why I sort of chose to bring in this one was that you might actually get into this situation because now you're suddenly dealing with more, not necessarily raw memory, but sort of more raw stuff. You'll be sending in, void pointers to OpenGL, etc. So it's something that can happen if you're not careful. So any questions related to this issue? No? Cool. So how do you fix this?
First, cast G into something that's 64-bit.
Casting it?
At least make sure when you're casting something into the void pointer, it's 64-bit.
Yeah. Okay. Yeah, okay. So what we can do is we're sort of going to do that. The way we're doing it is that instead of doing it directly that way, we're just going to declare this as a void pointer. There. And then we'll not do this cast here. There, and then we should suddenly get some other error. And the error now is, subscript requires an array of pointer type. That's essentially down here. Because now we sort of get into the other issues. This is just sort of cleaning up. We have two problems here. The first one is that we can't convert the offset. It's a void, so a void pointer, so we cannot actually convert it to an integer. What we'll do is that we'll use this super nice macro thing, which is let's see, and then also like well, I'll go and check in the correct one because I don't remember what that macro is. It's a sort of way to print out a specific type that we're going to need. There we go. Because what we're going to do is that we're going to start casting this over to something else, an int pointer, which is essentially just an integer that is guaranteed to be large enough to hold the value of a pointer. So it's not a pointer, it's just something that can hold sort of the value of a pointer. And then we'll do the same here, because we can't add a void pointer to everything because that doesn't make sense. We don't know how big it is or anything. So we're doing the same here. And now, hopefully, we'll get the same or the correct results. Yeah. Cool. Any questions?
If you go back to where you declared the variable,
Yeah.
to a pointer,
Yeah.
you could just can you just declare that a pointer to a pointer if you add an extra asterisk, would that work? And then not cast it?
So,
Like not do the integer pointer cast.
oh right, no, that won't fix this issue, and it will introduce another issue, which is that if we set this to null, then it's a null pointer, which is trying to write to, and if we don't initialize it at all, then we're sort of saying, hey, go write this variable somewhere in memory that we don't know where it is. So, with that, it's 1 o'clock, so let's take a break before we look at the two next bugs, unless there are any questions.
How long a break?